Alright, in this video we'll be continuing with our discussion of adding capacitors to an AC circuit, and we're going to explain a certain phenomenon that happens to the voltage when we add components to an AC circuit that has a power supply, okay? And so this is to do with Kirchhoff's voltage law. Okay, so like I said in the intro, we're still looking at AC plus capacitors, okay? So capacitors within an AC circuit, and the circuit that we're going to look at is what's called an RC circuit, okay? And so what this circuit is if we have our AC power supply. This circuit is when we have a resistor and a capacitor in series in an AC circuit, okay? And so we have a resistor with a resistance of R and a capacitor with a capacitance of C. And so as you can see, this is where our RC comes from in the name RC circuit. Okay, so pretty self-explanatory. Okay, so like I said in the intro, this phenomenon has to do with Kirchhoff's voltage law. So if you don't mind, we're going to go over a quick review of Kirchhoff's voltage law. Okay, so this is going to be a review. In DC circuits, we know that if the components are in series, that means that the voltage must be split across those components. And so let's say this has a 10 volt supply, okay, and let's say the voltage drop across this is A, and let's say the voltage drop across this is B. We know that from Kirchhoff's voltage law that 10 minus A minus B is equal to 0. In other words, 10 must equal to A plus B. Okay, and obviously this has to do with the conservation of energy, because we know that voltage is defined as the amount of energy per coulomb of charge, okay? So the problem that we have is that when we have an AC circuit such as this, what we find is that at face value, Kirchhoff's voltage law seems to be broken, okay? So let's say across our AC supply we get an RMS voltage of 10 volts, okay? And our resistance has an RMS voltage of 6 volts, okay? And our capacitor has an RMS voltage of 8 volts, okay? And so it begs the question, how is this possible? This clearly defies Kirchhoff's voltage law. Now, I'll show you at the end of this video, I didn't just pull numbers out my ass. These numbers do actually add up and make sense in the end. So I didn't just pick random numbers and say, oh, Kirchhoff's law is broken. No, these numbers do add up, but as you can see on face value, these numbers don't seem to add up and they seem to break Kirchhoff's voltage law. So I'll show you why they don't, okay? So the reason why this does not violate Kirchhoff's voltage law is because the voltage across our resistor and the voltage across our capacitor are not in phase, okay? Remember that these values are oscillating. All these values are oscillating. The source voltage is oscillating, the voltage across the resistor is oscillating, and the voltage across the capacitor is also oscillating. So all these values are oscillating, and what I'm saying is the voltage across the resistor is not in phase with the voltage across the capacitor. So what that looks like is if we were to have our graph over here, where this is our voltage and this is our negative voltage, if we were to have the voltage across our resistor, like so, okay, so this is the voltage across our resistor. If we were to monitor the voltage across our capacitor, what we would find is that it's actually lagging the voltage of the resistor by 90 degrees, okay? And so it would actually peak roughly over here, and we would get this sort of graph, okay? And as you can see, this forms the shape of a cos graph, and this forms the shape of a sine graph, and we know that a cos graph is equal to a sine graph just 90 degrees shifted. So that makes sense, okay? That this is a 90 degree lag. Okay, should probably draw this as a one-sided arrow, okay? So as we can see, this is the voltage across our capacitor, and it's lagging the voltage across our resistor by 90 degrees. Okay, so what this means is that even though the RMS value of the voltage across the resistor and the voltage across the capacitor does not equal to the RMS value of the voltage of the supply, at any specific instant of time, so at any time t, the voltage across the resistor plus the voltage across the capacitor will equal to the voltage across the supply. And so this is at any time, which we can denote as t, okay? So at any time of t. So if we pick any arbitrary time, let's say right here, okay? So at this value right here, we would have an arbitrary value of our voltage across our resistor and an arbitrary value of the voltage across our capacitor. And those two values right there would equal to the voltage across our supply at that same time. Okay? Another way to represent this scenario is to use a phasor diagram, okay? So if we were to draw our phasor right here, or our phasor circle, and we can start by drawing the phasor of the voltage across the resistor, okay? So I'm keeping the same color, so this is orange, this is our VR, okay? And we know that our phasors always go in the anti-clockwise direction, okay? So we should know that from our simple harmonic motion and our reference circles, okay? And because we said that the voltage across the capacitor is lagging by 90 degrees, the voltage across the capacitor will come down like so. And as we can see right here, there is a 90-degree lag. So the cool thing about this scenario is that we can use this phasor diagram to analyze or to find out the voltage of our supply at that same time, okay? And so our voltage of supply, that vector is going to be right here. Okay, so this is the voltage of our supply. And there's also an angle that we may be interested in right here, which we can call theta. So now it might start to become apparent that we don't just straight add the voltage values, okay, because 6 plus 8 does not equal 10. What we do instead is we add the vectors together. We do vector addition, okay? So in this case, we have our voltage across our resistor, okay, and we found out that that is 6 volt RMS, okay, and that's to the right. We have the voltage across our capacitor, okay, and we found out that's 8 volts RMS, okay, and therefore our supply is this resultant vector right here. And so as we can see, our supply voltage is equal to square root 6 squared plus 8 squared, okay, and so that's equal to square root 36 plus 64, and as we can see, 36 plus 64 is equal to 100, okay, so our Vs is equal to square root 100, and so therefore our Vs is equal to 10 volts. And as you can see, I indeed did not just pull numbers out my ass, they do add up. And as we can see, Kirchhoff's voltage law still holds up. Okay, so the main problem here was that we were using RMS values to try figure out Kirchhoff's voltage law. However, instead, we must figure out what are the voltages at a certain time, okay? And we can do that much easier using phase diagrams and therefore using vector addition to find out our voltage values, okay? And so that will be it for this video. See ya.